All right,
good.
we're live.
Hi Ravi, hoping you are doing
Sanjay.
well. Welcome on the board.
I'm doing well. Thank you.
We are running on the
Thank you,
fourth
Sanjay.
day of AI Expo, and thank you so much for accepting the invitation. So it is a pleasure to me, first of all, introduce about you to participants, and with your brief introduction here. So let me do it first, please. So, thank you everyone for joining here. We are running on the fourth day of AI Expo by Swarm Community, and I am Dr. Sanju Tiwari, Professor and CEO of Shodh Guru Research Lab. So, it is my pleasure to introduce Ravi Bajracharya. So, Ravi Bajracharya is the CTO and co-founder of the Datum, with over 15 years of experience in software engineering and a strong background in AI applications. Within the healthcare industry, Ravi specializes in modeling health data and biomedical knowledge bases for semantic representation using RDF triple stores. His expertise lies in bridging AI technologies with healthcare data to create intelligent solutions that support precision medicine. So today he is going to speak about knowledge augmented graph reasoner, a neuro-symbolic reasoning framework. So thank you, Ravi. Now please take over the session.
Thank you, Sanju, for the kind introduction. Let me share my screen real quick. Can you see my screen now?
Yes. No, not yet. Sorry. Can you please try again?
How about now?
Yeah. It's loading. Yeah, finally.
Okay, great.
Yeah.
Let me do this full screen. Hello, everyone. My name is Ravi Bajracharya. I'm the CTO, co-founder for Datum. My background is more in biomedical knowledge graphs and more in semantic triple stores, to be particular. And at Datum, that's what I've been doing. I build biomedical knowledge graphs from various sources in the healthcare and biomedical domain. And I build it to support different types of healthcare applications. So Datum is a connected health platform that brings together biomedical knowledge and health data for applications in precision medicine and decision support, and also in AI applications like generative AI, language models, and so forth. And today, I mainly wanted to touch upon a few challenges in adoption of AI in healthcare, particularly generative AI, and how guideline adherence is important for kind of building very reliable and trustworthy AI, and also in improving the adoption of AI in healthcare. And I'll be talking a little bit about reasoning and how that can actually help with the problem of guideline adherence. And particularly, I want to talk about a framework called the knowledge augmented graph reasoner that we have kind of built in Datum to be able to solve this problem. Finally, I'll touch a little bit on some evaluation benchmark frameworks that goes with this. So, implementing AI in healthcare is pretty difficult. The bar for success is pretty high because there's a lot of like regulatory red tape and compliance requirements owing to different reasons, which affect whether a particular model is acceptable for clinical use or not. Um, and uh, you know Also, there are a lot of challenges inherent in the way the models work. Um, like, for example, the generative models like LLMs are probabilistic, which makes them very difficult to be reproducible, and also um, inherently very limited in terms of its reliability in its responses. Um, at the same time, they have the problem of not being able to differentiate fact from fiction, and has have the problem of hallucinations, for example, um, that we are all aware of. Um, and also, uh, healthcare data quality also poses a lot of problem with AI model. Um, and there are inherent biases in the data that AI picks up, and as a result, uh, the model reliability and explainability kind of can be compromised as a result. So yeah, overall, it's pretty challenging to kind of make this work for healthcare. Um, and currently, the mainstream approach to solving this has been mostly a document based in context learning approach, where um, we provide a lot of documents to the model uh, as a context that can mitigate a lot of the challenges we see in the model, so that it does less hallucinations, and it has the right context to generate the right response. So, for example, the RAG is most popular, which takes all the documents, creates vector indices from them, and then uses a search um, to retrieve the right chunks of the document based on the query. This may not work well when you have complex documents where the context you need is spread across different documents, or um, are more interconnected. Um, that's where, like, the second approach that's becoming popular, which is a little bit more graph based, where a graph is constructed to link, like, interconnected concepts and context together, works a little better at kind of retrieving right context and then generating the relevant summaries. um, and this is very well suited for more query focused summarization tasks, rather than just kind of search based responses. Um, and in addition to that, we also have the uh, orchestration of different models to form more of an agentic flow, where you're taking multiple models that can coordinate together to be able to generate the response, and also that utilizes third party or outside tools to be able to kind of furnish a response. The advantage of this approach is it could be easier to make your models adhere to the guideline better with this approach, but the con is that it requires a lot of customization and also maybe developer input. Um, so, and one area where these current approaches struggle is with guideline adherence, and it's also the key to improving AI adoption in healthcare. In my opinion, particularly in mission critical domain like healthcare. Um, because, like, in healthcare, we have a lot of guidelines, from treatment guidelines to dosing guidelines to even like policy guidelines for healthcare procedures and so forth. So it is very important for models used in healthcare to be compliant with these regulations, standards and evidence-based guidelines. um, that's going to make the models more, you know, acceptable and more readily adopted in healthcare. And at Datum, like this is what we're trying to solve for, like, you know, how we could take language models and make them adhere to guidelines. Um, and for at Datum, like currently we are looking at the domain of pharmacogenomics, which is a subdomain within precision medicine, which kind of uh, deals with uh, drug gene interactions and has a lot of guidelines uh, that talk about different dosing requirements owing to how the drug is metabolized or how it interacts with different um, phenotypes of genes in different individuals. Um, so for this talk, we will probably look at one such guideline, which is for clopidogrel in relation to a gene called CYP19, and it's published by a body called CIPIC, which stands for Clinical Pharmacogenomics Implementation Consortium. And normally the guidelines, they highlight, like, you know, what to test and when to test for particular drug, and how you do like different doses adjustments based on the results, and if any alternate medication or consideration needs to be taken into account owing to those results, right? Um, so so if you look at a typical retrieval based approach, where we take a bunch of guideline documents and put through a naive rag system. um, So here, the approach is to more to find answers within the guideline using the query in question, um, and the query might be like, you know, for this patient who is of this age, has this disease and this history, what is the, like, you know, recommendation or whatever. So this approach doesn't work reliably with this approach, because most of the queries contain very specific patient details that are not in mentioned in the guideline specifically, or the guideline might need more domain specific knowledge in addition to just having the guideline there to infer more details based on the given details of the patient. Um, so as a result, the retrieval based approach does bring in chunks from the guideline, but it's not what the LLM needs to be able to answer the question. So it has very limited use for that. So we need to uh, rethink the guidance adherence problem more as a reasoning problem, where rather than as a search problem. So by that, what I mean is, like, you know, most of the guidelines um, mainly provide a framework to reason over the input data anyways, like uh, if we look at the previous guideline, we can actually reduce it to something like this, which kind of uh, gives you a very clear framework to reason through your input patient data to determine what the outcome should be. So instead of kind of just relying on the source to be able to pull in these right information from the guideline. So if you are familiar with something called the chain of thought or the tree of thought approaches, so this is kind of similar where um, so uh, instead of in the chain of thought, like you are prompting the language model itself to kind of generate the steps to solve the problem, but here you are basically extracting the reasoning steps from the guideline to be able to come to a recommendation based on that guideline, if that makes sense. um, so yeah, so basically I'm trying to highlight, like, you know, uh, uh, the guideline adherence problem can be thought of more as a reasoning problem than as a search and retrieval problem. Um, but there's still limitations to this approach in that, like, it is still lacking uh, domain knowledge of like pharmacogenomics, for example. So as a result, like, its ability to reason um, can be compromised. So it may not be able to uh, do a very good job in terms of producing the results. Um, so, uh, for example, like maybe it's trying to answer if the patient is a particular phenotype, um, but it might need the knowledge of like what types of gene alleles kind of form a particular diplotype, which forms a particular phenotype, for example. So this knowledge needs to be uh, available to the language model as context. So here, the framework is still missing the domain knowledge, and this is where what we have built comes in, which is a knowledge augmented graph reasoner. So it actually has three components. One is the actual flow that uh, is being extracted from the guideline. And the second is the knowledge graph that kind of encapsulates the domain knowledge for that particular guideline. So in this case, like, the pharmacogenomics, um, the CIPIC guideline, and any evidences that it's linked to, and so forth. So that forms the knowledge part. And the third part is more of a performance benchmark. Um, so so being able to kind of not just generate the flow, but be able to actually benchmark and see how well it is doing against a set of like test cases, for example. Um, so for the reasoner, we have a pipeline that takes in these uh, different guidelines. Um, so, like in this case, the CIPIC guidelines, and then it turns into a list of recommendations, which uh, is recommended through the guideline. And for its recommendation, it extracts a series of flows that leads to that recommendation, and then finally, it combines them into a something called a directed acyclic graph. So it's basically a flow chart, so to speak, which kind of has a start and a bunch of flows, and it kind of ends in a set of recommendations. So uh, I could quickly show how this might look like. Like, this is our platform, which allows people to kind of review like what is generated. So if you look at what is generated for clopidogrel based on this guideline, you can say it's almost like a questionnaire where it extracts like the decision points that leads to different uh, recommendations that are in the uh, 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 in the guideline, right? Um, so um, so yeah, like the first step is to be able to extract these flows, so to speak, from the guidelines. Um, and the second part is then being able to kind of look at individual steps in the flow and then augment them with the knowledge context. Like, for example, um, we can link the recommendations to the evidences that the recommendations are based on. Um, so in this case, it might be the guideline, or like the the other evidences that the guideline might refer to, um, or like some of the decision points steps in the in the flow might need more context about um, how to map, like, the input data to something else. So, like, the question might be to determine phenotype, like I was saying earlier. For that, it might need to map the genetic test results to the phenotype, and that might come from the knowledge graph, knowledge base, and not necessarily the guideline. So guideline may not have all that information in there. um, and to get an idea of how something like that might look like, it's like, okay, if you have a recommendation, for example, it can be linked to which guideline it comes from, and also how a particular phenotype is determined, what are different diplotypes associated with them. So these all can come from a knowledge graph to supplement the context for the language model. um, so the second step is to be able to augment your reasoners with the knowledge context. Um, and the one advantage of having a knowledge graph is also that it serves as an effective guardrail for your language model. So it can use a knowledge graph to kind of constrain the conversation within the context of that recommendation, or for that drug, or for that guideline, based on where the conversation kind of uh, goes to. Um, and the third part of the framework is more of a benchmarking framework, where it can generate test patient data and be able to kind of benchmark each of the flows to see how well it can reason over those test data, and give it a go or no go, based on the benchmark. Um, and the benchmark can also break down the the problem to uh, not just the overall flow, but to also individual steps in the flow that is causing that is having problem, so that um, someone can go into the framework and actually fix the flow, if the automatic extraction was not very good, or if it's lacking some context, right? um, so pretty much it's more of a rinse and repeat, where you automatically extract a flow, you add the context from the knowledge, you benchmark it, and then you diagnose and fix, um, and you again try to benchmark until your result is satisfactory, and that you can deploy to to the production or whatever. Um, and one advantage of this framework is that it very much allows a human in the loop, so someone can come in and review um, what the reasoning actually looks like, and not just something that's generated automatically by the language model at the inference time. So this gives uh, explainability, reliability, and also a human in the loop approach to this approach. Um, so from our benchmarks, we are able to improve the baseline GPT responses by 3 times, and also at the same time make it 5 times cheaper to implement, because it doesn't require like fine tuning, of or making a foundational model from the ground up. um, and it significantly improves your time to deployment, um, and at the same time you have uh, clinician validation in the process as well. um, so beyond healthcare, the use cases that we are looking at uh, is like any uh, use case that is very heavily dependent on kind of the need to adhere to guidelines, right? So it could be like regulatory, legal, so obviously healthcare, um, where you need more of a deterministic approach, and you need more of a human in the loop review, and ability to reason, and that's where this framework kind of uh, shines quite a bit. Um, So yeah, it in conclusion, uh, I would like to say like it's a pretty simple framework, but pretty effective, and we hope doing something like this can not only improve the adoption of AI and language models in critical domain like healthcare uh, and in clinical scenarios, but also um, solve the same similar problem in other domains like we looked at. Um, so with that, maybe I could take some questions if you have. Not sure if how much time we have left. I could quickly take some questions or comments.
Yeah, I would just ask, what are some of the next steps in commercializing this technology?
Um, so yeah, I think currently the framework we have is a little bit specific to pharmacogenomics. So um, I think we need to generalize it a little bit so that it you know it can go beyond pharmacogenomics into more broader. Obviously in healthcare you have uh, different types of guidelines, so it can handle uh, all types of guidelines, and also beyond healthcare also, right? And the second is like obviously the knowledge graph. So we need to kind of increase the domain knowledge into all these different areas so that it's able to provide the right context and improve the performance for the language model that way. Um, so yeah, I think uh, increasing the content and also making it more generalized. I think we need to do those two steps before we can uh, commercialize it.
Excellent. Well, thank you, Sanju, and thank you, Robbie, for taking part in this wonderful presentation. We're gonna take a brief
Mm.
break, and then we're gonna move on with the next presentation. Stay tuned for more.
Thank
Yeah,
you.
thank you.
Thank you for inviting us.
My pleasure.
Thank you again. Yeah.
Thank you, Ravi.